Hello everyone, this is the video for lecture 22. Today we are going to start chapter 23 on mirrors and lenses. We'll be continuing to use the ray model of light throughout chapter 23, and in fact, the study of mirrors and lenses is one of the primary reasons for even developing the ray model of light to begin with. The definition of a lens or a mirror, by the way, matches up with your everyday expectation of what it should be. A mirror is a piece of glass or metal that light can reflect off of, and a lens is a piece of glass or plastic that light can refract through. Looking at the picture on the right, you have an object that is emitting light in all directions. A few of the light rays outlined in blue are heading toward the mirror, they reflect off of the mirror, and then they enter the eye that's shown right here. Now this person is looking in the mirror, and they're not actually seeing the object. Right? To look at the object, they would have to look upward toward the object. What they're seeing is the image of the object in the mirror, or behind the mirror in this case. Now there are two kinds of images that can be formed by lenses and mirrors. At this point you can view the following as just two definitions for two different types of images. We will have plenty of examples coming up to help you understand what these things actually are. So the first one is a virtual image. This is where the outgoing light rays appear to originate from where the image is located. In this case, outgoing light rays means light rays that are reflecting off of the mirror. So you have three light rays outlined here. They're reflecting off the mirror and heading toward the eye. If you trace these light rays straight backwards to where it looks like they came from, then you have to trace behind the mirror, and you'll end up at the image location. Since these light rays do not actually originate from this image location, it's a virtual image. A real image, on the other hand, the outgoing light rays converge at an actual point where the image is located. So in the case of a real image, we can look to the human eye. An outgoing light ray in this case would be a light ray that has already refracted through a lens. So the light rays that refract in the lens of the human eye are considered outgoing light rays. These light rays actually converge on a single point. This will be the image location. In short, for a virtual image, the outgoing light rays do not actually meet. For a real image, the outgoing light rays do meet at a single point. One of the reasons we make this distinction is because real images can actually be displayed on a screen, like in a movie theater or a classroom projector. If we were in the classroom, I would point at the screen. The projector is projecting a real image onto the screen. Virtual images, on the other hand, cannot be projected on a screen, but they're also very important, and we'll see why in the next couple lectures. In the figure on the right, there are three important bits. There is the object, there is the mirror, and then there's the image location. This is the location where you would think the object is located if you were looking in the mirror. We defined the distance from the object to the mirror as p, the object distance. We define the distance from the image to the mirror as q, the image distance. Sometimes in other literature you will find the object distance labeled as o and the image distance labeled as I. So the object is the actual physical object that's giving off light. When you're looking in a mirror or through a lens, the image is where it looks like the light is coming from. So to clarify that, imagine that you're standing in front of a mirror and you have an object behind you. So imagine that this eye is your eye, and imagine that this object is a candle that's located behind you. So you have a mirror in front of you and you have a candle behind you. The actual object that's giving off light is the physical candle that's located behind you. That's the object. But when you're looking forward, you're looking in front of you, you see a candle in the mirror. So it looks like that candle is located in front of you in the mirror. That's the image of the candle. Contrast this with a similar example. You have an eye. You have, instead of a mirror, a window. And then you have a candle located on the other side of the window. That candle is an object that's actually giving off light. Some of that light is traveling through the window into your eye. So in this case, you have an object that's located in front of you. The image where it looks like the light is coming from is also in front of you. In this case, the object and the image are one and the same. In general, to find where the image is formed, you have to trace back at least 2 rays of light after they reflect in the mirror or after they refract through a lens. In the figure on the right, the light rays that are reflected are the ones traveling toward the eye. To find where it looks like these light rays are coming from, you have to trace them backwards in a straight line. So in this case, you follow the dotted lines back to the image. The point where those light rays converge, or where it looks like they converge, is the image location. Now I want to point out that I use the word carefully here. A lot of times what I'll see is, let's say with this example, you have 3 outgoing light rays and a student wants to find where the image is located, so they trace back the light rays, but they do something like this. They just trace back light rays, and the light rays never meet, so then the student concludes, well, there's no image here. Okay. In this case, it's easy enough to trace back the light rays because the dotted lines are there to guide us. But if you don't have those dotted lines, you have to be very careful about tracing back those light rays. The question at the bottom asks what type of image is formed in a flat mirror. The previous slide already gives us the answer. It's a virtual image. But let's see why. Back up in this figure, you have outgoing light rays. You trace these back to see where it looks like they came from, and they come from this point behind the mirror. This point behind the mirror is not physically giving off light rays, so it is a virtual image. Let's analyze this flat mirror a little bit closer in the lower left. You have a point source that's emitting light in all directions. So first of all, let's look at that light. This ray that's going into the upper right, it travels toward the mirror, it reflects off the mirror, and we know that for a flat mirror, the angle of incidence has to equal the angle of reflection. So that light ray reflects off the mirror at the same angle that it is incident upon the mirror. This is going to be true for all of the light rays bouncing off the mirror. The flat mirror specifically. Okay, so the work has already been done for us. All of these outgoing light rays have been traced backwards in straight lines, and they all meet at one location. This location is the image location. The object distance, P, is the distance from the object, the point source, to the mirror. The image distance is the distance from the mirror to the actual image. Oh, we'll use Q for that. In the case of a flat mirror, it's always true that P is equal to Q. That means the image formed by a flat mirror is an equal distance behind the mirror as the object is in front of the mirror. This last bullet point is a consequence of the law of reflection. It says that basically you have a light ray that comes off of an object, like this man's shoes. The light ray is going to eventually go into his eyes. In order for that to occur, the light ray has to bounce off the mirror at the point that's halfway between his eyes and his feet. Right there. And that is because theta r is equal to theta I. You could prove this midpoint rule is true using geometry, and this statement that P is equal to Q. You could also prove this with geometry, but as far as I'm concerned, we'll just take these as facts and move on. Although I do want to point out that P equals Q is only true for flat mirrors. If you're talking about lenses or curved mirrors, we have something called the lens equation that we'll use to relate P and Q with each other. And finally, these diagrams where I'm drawing all the objects in the image and the light rays, these are called ray diagrams. And that leads us to our first question. You have an object placed in front of a mirror. The mirror is positioned to the right of the object, and you have an observer to the left of the object. Which of the points A, B, or C indicates where the observer would perceive the image to be located? If you've been following along the previous few slides, you may think the answer is obvious, but this is also a good chance to practice drawing a ray diagram. I will give you the answer to this in one of our meetings. In this question, you have two observers. Observer 1 sees the rock in the mirror, and for observer 1, the image is located at position C, directly behind the mirror. The question asks, where does observer 2 see this image? Now, when you're thinking about this question, I don't want you to just guess, because I find that although it seems like a simple and straightforward question, oftentimes students will get this wrong. So rather than just guessing, I want you to actually draw the ray diagram using the rock, the mirror, and observer 2. So do that, find the image that observer 2 sees, and I will give you the answer to this in one of our meetings. Aside from flat, plane mirrors, we'll also be considering spherical mirrors. A plane, by the way, in this context is P-L-A-N-E, like an XY plane, so it just means a flat mirror. In any case, we will also be considering mirrors that are spherical, and there are two types of spherical mirrors. The first one is a concave mirror. This is the mirror shown on the left. This type of mirror takes incoming parallel light rays and it causes them to come together at a single point. So you have a green object here that I'm outlining in red. This object is emitting parallel light rays. They're all traveling to the right and they are parallel to each other. After they reflect off the mirror, all of these light rays converge onto a single point. Concave mirrors, you can remember the name concave because it has an inward curve. It curves inward like this, so it goes in like a cave. Another name we used for concave mirrors is a converging mirror, and that's because all of these light rays converge to a single point. By the way, if you're looking at these parallel light rays and to you it looks like they're bending away from each other, like they're not parallel, that is an optical illusion. They are actually parallel to each other. The second type of spherical mirror is a convex mirror that's shown on the right side. This type of mirror takes those parallel light rays, and after they bounce off the mirror, all of these light rays spread out. So they diverge away from each other. Because of this, we also call this a diverging mirror. And diverging mirrors have this outward curve. Spherical mirrors are named as such because they are part of the surface of a sphere. In the cases shown, you have actually half a sphere. In this case, the right half of the sphere. It doesn't always have to be half to be a spherical mirror, just these examples are. The radius of the sphere we call the radius of curvature. So if you draw a line from the outside of the sphere to the center, that radius is called the radius of curvature. The center of the mirror, or the center of the sphere, would be called the center of curvature, labeled C. The focal point for this mirror is where the horizontal light rays meet. In the case of a concave mirror, all of the light rays actually meet at a single point. This is the focal point for a concave mirror. For a convex mirror, the outgoing light rays do not actually meet at a point. So what you have to do is trace all of the outgoing light rays backwards, the outgoing light rays being the ones that have already reflected. So here, for instance, you have one outgoing ray. You want to trace this one backwards in a straight line. Here you have another outgoing ray. You want to trace this one backwards in a straight line. And then you can do this for as many as you want to. 2 is good enough to see that the trace back for these outgoing light rays will meet at a single point. So for a diverging mirror, the focal point is actually going to be behind the mirror, to the right of the mirror. The focal length is the distance from the mirror to the focal point. For the concave mirror, it is that distance, and for the convex mirror, it is just this distance. Now again, it's just a matter of fact that you can show that the focal length is 1/2 the radius of curvature. This is something, again, I do not intend to prove, but for a spherical mirror, we will just take it as true. You can actually fit flat mirrors in with this concept of spherical mirror as well, if you consider a flat mirror to be part of a sphere that has an infinite radius, in which case the focal length of the mirror would also be infinite. But this is probably not too important to know. We want to study objects and images in the context of these spherical mirrors. So we want to draw ray diagrams for these spherical mirrors. To do this, I want to be very careful with the rays that I'm drawing, so I'm going to take us out of presenter mode and put a ruler on the screen. The idea is going to be similar to what we did with the flat mirrors. I have an object, in this case an arrow. Let's say that this arrow represents a candle. So I have a candle, and at the top of the candle I have the flame, and that flame is emitting light in all directions. I need to study how this light comes or goes toward the mirror, reflects off of the mirror, And then I have to study those outgoing reflected light rays. In the case of concave and convex mirrors, and even lenses coming up, there are 3 particular light rays that make this job easy for us. So rather than considering every single light ray that's coming off of this candle, I only have to consider these 3. The first is the horizontal light ray that's coming off of the candle. So I'm going to put my ruler up to the top of that flame. I'm going to draw the horizontal light ray that's coming off of that candle and going toward the mirror. When that light ray reflects off of the mirror, it's going to head toward the focal point. So that one particular horizontal light ray reflects off the mirror and goes through the focal point of that mirror. This is F, the focal point. Okay, that's the first easy to draw light ray. The second easy to draw light ray is the one that starts at the top of the candle and goes directly toward the focal point. So I line up my ruler. I have a light ray that goes straight from the top through the focal point and hits the mirror. After that particular light ray reflects off of the mirror, it will be horizontal. And let's draw some arrows here too to represent the incoming and outgoing light rays. Okay, the third easy to draw light ray is the one that strikes the very center of the mirror. So I'm going to line my ruler up with the top of the candle and the center of the mirror. Draw the line, draw the light ray from the top of the candle to the center of the mirror. And then after this light ray reflects, it's actually going to follow the law of reflection because it hits that one very special point of the mirror. So it's going to reflect off the mirror at the exact same angle that it hit the mirror. And it'll reflect off in this direction. So I have incoming, outgoing. Incoming, by the way, in this context means it's incoming toward the mirror, and outgoing means it's outgoing from the mirror. Okay, so in the case of that third light ray, I have law of reflection, shows me that the angle of incidence equals the angle of reflection. The first 2 easy to draw light rays, by the way, the horizontal light ray and the focal point light ray, these both follow the rules from the previous slides where I have horizontal light rays bounce off and go toward the focal point. That one in particular explains the first one. The second easy to draw ray is just taking that idea in reverse. You have a horizontal ray that would reflect and go toward the focal point, which ends up at the top of the candle. Now, just to be clear about which light rays are which, I have redrawn the light rays color-coded. So you have light rays emitting from that candle in all directions. There's 3 very special light rays that give you an easy to draw ray diagram. The first one, the red one, is the horizontal light ray that goes toward the mirror. When that one reflects off the mirror, it reflects and goes through the focal point. The second easy to draw light ray is the light ray that starts at the top of the candle and goes toward the focal point. When that one reflects, it's horizontal. The third one in purple is starts at the top, goes toward the center, and it reflects off at the same angle. So we call these the horizontal to focal point light ray, the focal point to horizontal light ray, and then the ray striking the center of the mirror light ray. Notice that all three of these easy-to-draw light rays meet at a single point. That point will be the image location. So if you were looking in this mirror, let's say that you're located somewhere around here, and you're looking in this mirror, and in the mirror you see a candle. You don't see the actual candle because it's behind you. What you do see is an image of the candle located at this image position. Also, since the outgoing light rays are actually meeting at a single point, this will be a real image. So down here it says the image forms where the rays meet. You may have to trace them back. In this case, you do not have to trace them back because they all meet at one location. Okay, and then one more thing on this slide. The three easy-to-draw rays give you an easy way to find where the image of the object is located. However, any light ray that comes from that candle and reflects off of the mirror will go through that image location. So for instance, if I draw just some random light ray that's going from the candle to the mirror, after this light ray reflects off of the spherical mirror, it will reflect off and go to the image location. Similarly, if I draw one that's going down lower, it goes toward the mirror. When this one reflects off, it will also pass through the image location. So the three easy-to-draw light rays are an easy way to find the image location, but then once you've found the image location, you know that every single light ray coming from the object and reflecting off of the mirror will go through that image location. And actually, one more thing before I move on, because you may be wondering, how come the third special ray, the one that strikes the center, how come this is the only one that obeys the law of reflection? Well, they actually all do behave according to the law of reflection. Let's go with the horizontal ray, for instance. The horizontal ray reflects off the mirror, and it actually does reflect off at the same angle as it hits the mirror. It's just that your normal line is at an angle. So for instance, maybe it looks like this. And then you have the angle of incidence is equal to the angle of reflection. This is true for all of the light rays that I've drawn. It's just harder to see for some of the light rays. The easiest light ray to see it for is definitely the light ray that strikes the center of the mirror, because then in this case the normal line is simply a horizontal line. So this is the ray diagram for a concave spherical mirror where the object is located to the left of the focal point. You have the object on the left here, the focal point is located right here. In the next question, you have a similar setup. You have an object, you have a concave spherical mirror, but this time the object is located between the focal point and the concave mirror. You have the focal point on the left here, and then you have the object between that and the mirror. Now I am going to work through this question with you because I think the answer is not as straightforward. But it would still be nice if you tried it before you listen to the answer. So I'm going to give you a second to pause and then come back and listen to it when you're done trying. Okay, according to the hint it says we should start by trying the first and third easy to draw rays. So the first easy to draw ray is the horizontal ray. So we start at the top of the candle and we draw the ray that goes toward the mirror. It reflects off the mirror and goes toward the focal point. The third easy to draw ray starts at the top of the candle. It reflects off the center of the mirror. It reflects off at the same angle. And heads out. The second easy to draw ray is not particularly easy in this case, but we will come back to that later. First though, I want you to notice these outgoing rays. They are heading away from each other, right? For comparison. This purple ray and this red ray will never meet each other because they're spreading apart. So in order to find the image, we have to actually trace these rays backwards. We'll start with the purple ray. We want to trace it backwards from the reflection point in a straight line. And then we want to trace back the horizontal ray, the reflected ray. So we trace back the outgoing ray from the point of reflection in a straight line. And if we trace them back far enough, you can see that the trace backs actually meet at one single point. So the trace backs meet right here. That point where the trace backs meet is the image location. So if you were looking in the mirror, you would see an image of that candle located at this position behind the mirror. So 2 of the easy to draw rays were enough for us to determine the image location. As a general rule of thumb, this is true all the time. In fact, the first and the third easy to draw rays will often be the easiest to draw. So when you're drawing a ray diagram, I would generally start with them. However, it can still be useful to draw that second easy to draw ray. And maybe there are situations where that second ray is easier than, say, the third ray. So let's talk about that one. I want to draw the ray that goes through the focal point and reflects off horizontal. Notice that if I start at the candle and I head toward the focal point, this blue ray is never going to reflect off of the mirror. Okay, this is why the second ray is difficult in this case. Rather than going from the candle to the focal point, this ray has to look like it's coming from the focal point and then go from the candle to the mirror. So the ray, the one particular ray that's going toward the mirror, let's use the cursor, this ray that's going toward the mirror looks like it's coming from the focal point. When this ray reflects off of the mirror, it reflects off horizontal. Now, in a perfect world, if I were to trace back that third outgoing ray, I would trace it back and all of the rays would meet at a single point. The moral of the story, though, is that two of the easy to draw rays are enough to determine where the image location will be. For a convex mirror, we follow a similar procedure. The three rays will look different, but they still follow the same rules. So we start with the horizontal to focal point ray. This one starts going horizontal. It reflects off of the mirror. And now we know it's a diverging mirror, so it has to reflect off in that direction somewhere. To determine exactly which direction it is going to reflect off, we have to make it look like it's coming from the focal point. So after it reflects, it looks like it came from the focal point. That's why it's the horizontal to focal point ray. The second ray in this case, the focal point to horizontal ray, this one will start at the top of the candle. It's going to head toward the focal point. Once it reflects off of the mirror, it will reflect off so that it's horizontal. And then the third ray is the one that still bounces off the center of the mirror. Bounces off the center, and then it reflects at the same angle that it bounced in at. And the third ray looks like that. To find the image of the object in this mirror, I again want to trace back all three of the outgoing rays. The red ray I have already traced back in order to determine which direction it was going outward, so that's done for us. To trace back the outgoing blue ray, I draw a horizontal line behind the mirror. And then the third ray, I want to trace back. The third outgoing ray, I want to trace back in a straight line. And here you have three rays that appear to be coming from the same location. These three actually do appear to meet with each other right around this point. So this is going to be our image location. Again, if you're looking in the mirror, you will see an image of this candle right here behind the mirror. In the first concave example 2 slides back, when the object was located to the left of the focal point, we determined that the image of the object was real. In the second example of the concave lens, or mirror, where the object was between the focal point and the mirror, in this case, the light rays did not actually come from the image location. They only appear to come from here. So in this case, we have a virtual image. And then in this third example with the convex mirror, again, the light rays do not actually converge on the image location. Instead, it only looks like the light rays are coming from this single point. So again, we have a virtual image. For the convex mirror case, we do not have 2 separate cases for the focal point. There's only one case for the convex mirror, and there's 2 for the concave mirror. Here's a question for you to actually think about. So you have an object, a green arrow. This object is emitting light in all directions. One particular ray is shown in green. This ray heads toward the mirror, and it's heading toward the mirror as if it were going to hit the focal point behind the mirror. Which of the 4 rays drawn represents the outgoing light ray from the incoming green light ray? Think about it, and I will give you the answer during one of our meetings. This question has a similar setup. You have an object, you have the convex mirror. In this question, you are asked to find the position of the image. So you have to draw a ray diagram. You can pick 2 of your favorite rays, 2 of your favorite easy to draw rays, draw those and trace them back and try to determine where the image is located. And I'll give you the answer during a meeting. After you've determined the image location, the follow-up question is, what kind of image is this? For a flat mirror, we had an easy relationship between the object distance and the image distance. For concave and convex mirrors, it's a little more complicated. Instead of just P is equal to Q, we have to use this lens equation. So in this equation, F is the focal length of the lens. Whenever you're dealing with a converging lens, F is greater than 0. So if you have a concave lens, you have to use a positive value for F. If you're using a convex lens or a diverging lens, you have to use a negative value for the focal length. P is the object distance. That's the distance from the object to the mirror. When we're dealing with a real object, P is greater than 0. Most of the time in this class, we will be dealing with real objects. There is one case in particular in lab where we will have a virtual object. I don't want to deal with virtual objects too much, so I'm going to skip over that for now, and I'll talk about that more in lab. Q is the image distance. For a real image, we have to use a positive value of Q. If the image is virtual, Q is less than 0. Okay, so for the object, P less than 0, basically this means if the object is located to the left of the mirror, then P will be positive. For the image, if the image is located to the left of the mirror, then Q will be positive. If the image is virtual and located to the right of the mirror, then Q will be negative. Okay, I realize that's a lot of words that may just sound like they're jumbled together, but I do have a table in a few slides that hopefully summarizes this for you. In any case, the lens equation is 1 over the object distance plus 1 over the image distance equals 1 over the focal length. And all 3 of FP and Q are always measured from the center of the mirror. And 2 more things. First of all, I said P less than 0 earlier. I meant to say P greater than 0. And secondly, this is called the lens equation because it is true for lenses, but it is also true for mirrors. Nonetheless, we called it the lens equation, or the thin lens equation. You may have noticed in these ray diagrams that the image height is often not the same as the object height. If you've ever looked in a funhouse mirror, you've noticed this as well. Oftentimes, curved mirrors can magnify things, either make them larger or shrink them in size. So the magnification of a mirror relates the heights of the object and the image. The height of the object, we just use the symbol H for. For the image height, we use H prime. Then the amount that a mirror magnifies an object, M, is given by H prime divided by H. So the image height divided by the object height. Using geometry, one can show that H prime over H is equal to minus Q over P. The minus sign here is actually a style choice based on how we define the lens equation. This is not necessarily the same as you will find in all sources, but we have to be careful to keep it in there. The object height h will be greater than 0 whenever we start with an upright object. This is going to be the vast majority of the time. In the unlikely event that we ever start with an object that is pointing below the x-axis, then we would have to use h less than 0. For the image height, if the image is above the x-axis, so if it's an upright image, then h prime will be a positive number. If the image is inverted, then h prime will be a negative number. We did actually see one example with an inverted image. The first example of the concave mirror where the object was to the left of the focal point, that had a real inverted image. So h prime for that example would have been negative. Now, rather than deal with this minus sign in the equation, oftentimes it's easier to just write that the absolute value of the magnification is equal to the absolute value of q over p. Oftentimes it's easier just to ignore that minus sign in the equation and then determine whether the q over p should be positive or negative after the fact. And this fits in with the next point too. If the magnitude of the magnification is greater than 1, then the image is enlarged. So it is increased in size. For example, if, say, the absolute value of m was equal to 2, then using the equation at the top, I could say that 2 was equal to h prime over h, and then I can write h prime is equal to 2 times h. And this last equation tells me that the image height is 2 times the object height. So the image is twice as tall as the object. Similarly, if the magnitude of the magnification is less than 1, then the image has shrunk in size. So for example, if the absolute value of m is 1/2, then I can write 1/2 is equal to h prime over h, and finally h prime is 1/2 times h. And this final equation tells me that the image height is half the object height. So the image has shrunk by a factor of 1/2. If we use this absolute value equation instead of the equation at the top, then we can determine after the fact whether m should be a positive or a negative number, basically by determining whether the image is upright or inverted. If the image is upright, then m will be positive, and if the image is inverted, then m will be negative. There have been a lot of rules on the previous few slides, and the table on this slide summarizes them. For example, the magnification m, the last thing I said about the last slide was that if you have an upright image, m will be positive, and if you have an inverted image, m will be negative. So then this table gives you a quick summary of all those rules I explained. This slide shows you the 3 different types of ray diagrams that we've gone over today. You have 2 for the concave mirror, one where the object is to the left of the focal point, and one where the object is between the focal point and the mirror. And then you have the 1 type of ray diagram for the convex mirror. These ray diagrams, rather than using the 3rd easy to draw ray that I was talking about, the one that bounces off the center of the mirror, instead of using that ray, they use one that goes through the center of curvature, bounces off the mirror, and goes straight back. You can use that one too. That's another easy to draw ray. In my opinion, I prefer to basically ignore the center of curvature altogether and use just the focal point. But there's another one for you if you would like. So you have these three diagrams for reference. I believe, though, that if you practice drawing the ray diagrams a few times, you just learn the techniques on how to draw them, then you can actually draw your own ray diagram quicker than you can look back to the reference. You know, search through the slides to try to find the reference, but it's up to you. Also, this slide shows you what you will see when you look in the mirror. On the left, the upper left, you have a concave mirror where the object is located outside of the focal point. If you were to look in the mirror at this bottle, you would see an inverted image of the bottle. This matches up with what you would expect from the ray diagram. In the bottom left, you have a concave mirror where the object is between the focal point and the mirror. If you look in the mirror, you'll see that you have an enlarged virtual image. This is what you expect from the ray diagram as well. Notice that we call it a virtual image, but it's something that you actually see. So it's not a fake image, an imaginary image, or anything like that. It's an actual image that you can see in the mirror. It's only called virtual because the outgoing rays do not originate from that location. And then finally, you have a convex mirror. If you look in the picture, you'll see that you have a very small image of the bottle. This is what you would expect from the ray diagram. So everything seems to match up here. So I do ask a question on this slide. I ask which type is used for side view mirrors? Which type of these two mirrors, concave or convex? The passenger side mirror in particular is not a flat mirror. It is either concave or convex. My hint to help you work through that is that the passenger side mirror says, objects in mirror are closer than they appear. This is a really cool example to demonstrate images and objects. And it's one that I'm really disappointed that I can't show you in person. What you would normally see in person, I have this black sort of flying saucer shaped device. There's a small hole cut in the top of it, and inside it is lined with mirrors. If you look at the right angle, you can see a frog that looks like it's floating on top of the UFO. In reality, you can see the actual frog is at the bottom here, sitting on the bottom, but the image of the frog is being projected up above this black UFO, and it's a really impressive sight to see, and it is unfortunate that you guys can't see it. So, you know, if I ever see you guys again, remind me to bring it, and I would be more than happy to. In any case, here's how it works. You have two very specially shaped mirrors. They're shaped like parabolas, like from math class. You have one parabola pointing upward on the bottom, and you have a second parabola pointing downward on the top. Now, if you put an object in the bottom middle of the flying saucer, then every light ray that comes off of this object will reflect off the mirrors in such a way that they all focus to one image location located right above the flying saucer. So first of all, since the outgoing rays do actually meet, this means the image is real, if you remember the definition of real image. Also, if you remember, I said that real images can be projected onto a screen. In this case, you're projecting the image right above the opening of that miroscope. If you then look at the miroscope at the correct angle, it'll almost look like there's a frog floating on top. It's sort of a holographic effect to make it look like there's a frog actually floating on top of the miroscope. If you do ever get the chance to see it, it does work best when there's plenty of light. The image at the bottom is just one that I took to show you as an example, but this really doesn't do it justice. I also found a video that shows you a little bit better what I'm talking about, but it also does not quite do it justice. So here you can see him setting it up with a screw. He puts a screw in the bottom, he puts the top on the miroscope, and then when he points the camera at it at the correct angle, it looks like that screw is just floating right on top of the miroscope. You can even see the reflection in the screw, like it's floating on a mirror that's sitting on top of the miroscope. In fact, you can even see the camera is focusing on the image from the object, the image that's being projected. This slide shows you the same idea, just with a few different points on the frog. And then finally, I will leave you with a few examples for the quote-unquote discussion section. In all of these examples, you are essentially asked to use the lens equation to find some different variables. I did want to point out, though, in the example 23.4, if you happen to have a cosmetic mirror at home, then you can even see this for yourself. Back on this slide, if you're far away from the cosmetic mirror, you should see an image of yourself inverted in the mirror. If you get closer to the mirror, you will see an enlarged image of yourself that is upright. And all of these examples give you some good practice with all of those confusing positive and negative rules that I summarized in that table. So I really do recommend that you go over them. And of course, if you have any questions, please let me know. Otherwise, have a good one.